Let's start the continuation of the lecture. So first I will define a signal. What is meant by a signal? A physical quantity which contains a meaningful information. So whatever the signal which contains a meaningful information is called a signal. For example, voltage with respect to time is a signal, or temperature with respect to distance is another signal, and velocity with respect to time is also one of the signal. Okay, so how to represent graphically? So let us say voltage signal is my DC signal. Okay, T 5 volts. So 5 volts DC signal. I will represent like this. A temperature with respect to distance. Let us say x distance. So at origin, let us say at x is equal to 1, the distance. So let us say 1 meter from the origin. We have a temperature of 20 degrees centigrade. Let us say x equal to 2 meter, 30 degrees centigrade. X equal to 3 meters. We have 40 degrees centigrade. X equal to 40 meters. We have, let us say, 10 degrees centigrade. This is also, let us say, temperature. This is also a signal. This function of x, t of x. Okay. Next, system. I will give a definition for the system. So it is like a device. This is a system which can do some operations on input signal and give some output. Okay, it's a physical device. It may be a low pass filter, it may be a high pass filter, it may be a delay system, it may be a squarer, whatever. Suppose y of t equal to log of x of t, which means this system will do the operation on x of t as log of that input, or if it is y of t equal to e power x of t. So the system will do on x of t an operation called exponential. Like that, let us say y of t equal to x of t minus t naught. So the system will do an operation on x of t input as input. What is that operation? Operation is a delay. So it will apply a delay to the input x of t. This is a delay system. So system is a physical device, or sometimes it is also a program. If it is a discrete time system, sometimes it is also a program. Okay, so it is not physical device at that time. Okay, So I would physical device or a program. Okay, which are I will say a hardware or a software which can operate on input and gives output. Okay, so these are the definitions for signals and systems. Okay, next I will go to the classification of signals and the classification of systems. First I will go to classification of signals. Classification of signals. So first classification, continuous and discrete time signals. Second, analog and digital signals. Third, deterministic and non-deterministic signals. Fourth classification, is periodic and aperiodic signals. The fifth classification, real and complex valued signals. And in this, in real case, even and odd signals, and in complex case, even conjugate and odd conjugate. Okay, so real and complex valued signals. So in real case, in real signals, there are two types of signals, even signals and odd signals. In complex valued signals, there are two types, even conjugate symmetric signals, odd conjugate symmetric signals. Okay, and one more classification, important classification. Seventh one is power and energy signals. These are some classification of signals, and there are no causal signals and non-causal signals. Okay, causal and non-causal signals will not exist. Causal and non-causal systems exist. Okay. Okay. Next, so I will define each and every classification of the signals. First one, the continuous and discrete time signals. So first one is continuous and discrete time signals. Okay, so first, continuous time signals. In continuous time signals, the time t is continuous. So what does the continuous mean? Continuous means the independent variable t takes all real values. How many real values are there? Minus infinity to plus infinity. So that is infinite values are there. Okay, so t takes all values. Okay, real values. Or suppose if t takes some interval, some 0 to 1. Okay, so these are the values t takes. So it won't take discrete values, discrete time values. Okay, it will take, if I mention this is a continuous time signal, the time takes all continuous values, all possible real values. So these possible real values are maybe integers or non-integers. So in between 0 and 1, how many values are possible? Infinite values: 0, 0 0.1, 0 0.2, and 0.2223, and so on, all up to 1. These are infinite values. Okay, that is the meaning of continuous time. If I mention continuous, so the time takes all values, integer or non-integer values, all real axis values. Okay, so I will give you an example. Example of continuous time. This time is continuous. Okay, the signal is defined at each and every point of time. Okay, so I will say like this. Okay, so between 0 to 1, let us say, so between 0 to 1 we have infinite values, but at each and every point between 0 to 1 the signal is defined. Okay, so between 0 to 1 this is the signal. So but each and every point we have signal strength, signal value. Okay, so this is called continuous time signal. Next, discrete time. Discrete time signal, the time is, the time axis is integers. It is finite values. are countably infinite. So what is the meaning of countably infinite? Countably infinite means, suppose we take natural numbers 1, 2, 3, 4, 5, and so on, infinity. Okay, so those are integers 1, 2, 3, 4, 5, 6, and so on. Okay, suppose if I take up to 1000, 1 to 1000, so they are large in number, but they can countable. Okay, so if I take some 10 lakh points, those are also countable, and so on. Okay, so even though the number of points are large, they are countable. So that means that is the meaning of countable infinite. So we can count. Or finite values. So finite values means not too many, not infinite values. Okay, some 1000 values, or some 50, some 100 samples, some 1000 samples, like that. The finite values. So time takes only integers. Okay, so for example, this is time axis will represent in terms of n, because n is an integer. So let us say signal a 0, this is like this, to 1 like this, 2, 3, 4, 5, 6, let's say it is 7, like this. Okay, but the time axis is integer values 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. -1, -2, -3, -4, -1. All these are integers. This is x of a discrete time signal. But the amplitude is not finite. Okay, it can take any value between 0 to infinity, or minus infinity plus infinity. This, let us say this value is some 10, this value is some 12, some 14, some 16, 14, 12, 10, any value 0 to infinity. Okay, it may be up to some 1000. Okay, whatever. So amplitude is not finite. Okay, it can take any value, but the time axis is finite. So here I will write, so time axis is integers, but amplitude is not finite. It can take any value. Okay, it can take any value between minus infinity and infinity. And in the continuous time case, in the continuous time case, this is the continuous time. In this case, the time takes all values between minus infinity and plus infinity, and amplitude also any value. Amplitude, let us say here 10 volts, let us say here 20, or some other case some 40, 100, whatever. So amplitude takes any value between minus infinity and plus infinity in continuous time case. In discrete time case, time is integers. Okay, so between 0 and 1, there are actually, in continuous time case, infinite values are there, but in discrete time case, between 0 and 1, only 0 and 1 values. Between 0 and 1, no other value is there. Okay, only 0 and 1. So this is the discrete time signal. The next classification, second classification is analog and digital. Analog and digital signal. First, what is analog signal? So in case of analog signal, amplitude is any value between minus infinity comma plus infinity. But time is both either continuous or discrete. Okay, I'll give you examples. So amplitude is any value between minus infinity and plus infinity, but the time axis is either continuous or discrete. Suppose the time axis is continuous. Okay, then amplitude is any value between minus infinity and plus infinity. So this is like this. Any value, this amplitude, any value between minus infinity and plus infinity. Say some x of t. Now one more example, if the time axis is continuous n, say x of n. So let us say t equal to 0, this value is 10, t equal to 1, 2, 3, 4, 5 and so on. So time axis is discrete. So but amplitudes may take any value. These amplitudes may take any value. Okay, 20, 30, 40, 20, 30, 40, minus 20, minus 30, sorry, plus 20, plus 30, minus 40 and so on. Okay, so amplitude is any value, but the time axis is discrete here. So analog signal means either continuous time or discrete time, but the amplitude is minus infinity to plus infinity. Okay, it is not finite value. Question: digital signal. In digital signal, the amplitude is finite. Amplitude is finite. Okay, we have to specify how many amplitudes it will take. Okay, 2 amplitudes, 3 amplitudes, 4 amplitudes, and so on. But they are finite. And time is either continuous or discrete. So I'll give example. Suppose time is t, continuous. Okay, then so amplitudes should be finite. Suppose I will take amplitudes like this. How many values it is taking? Let us say this is some signal. Suppose some d of t. Okay, time is continuous. So let us say this is a. So the amplitudes here either a or 0. That's it. T equal 0 to, let us say here some 1 second, 2 second, 3 second, 4 second, minus 1, minus 2, minus. Between 0 to 1 it is taking a, and 1 to 2 it is taking 0, and 2 to 3 it is taking a, 3 to 4 it is taking 0. So that is the amplitudes are finite, either a or 0. So only 2 values are possible, or it may take 3 values. So let us say plus a, minus a and 0. Okay, amplitudes. plus a minus a and 0 are 4 values, a, 2a, 3a and 4a and so on. So this should be a finite set of amplitudes. This is called digital signal, but the time is continuous here. Time is continuous. And I will give you one more example for discrete time. So n is discrete. Let us say, I will say d of n. So 0, 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 1, and so on. Okay. So then the amplitudes should be finite values. Okay. At 0, let us say a. At 1, let us say 2a. At 2, let us say minus a. At 3, let us say 3a. So 1, 2, 3, 4 values it is taking. And at 4, let us say a. And at 5, let us say minus a. At minus 1, let us say 2a. No. At minus 1, let us say minus a. At minus 2, 2a. At minus 3, 3a. And so on. So only amplitude values are here. Amplitude values are minus a, 2a, 3a. So a set of 4 numbers. That's it. But the time is discrete. Okay. So this is digital signal. So either time is continuous or time is discrete. This is digital signal because it is taking finite values of amplitudes. Okay. So I will summarize these things. Analog, continuous time. Analog, discrete time. Digital, continuous time. Digital, discrete time. So these are 4 possible ways to represent the signal. Okay. So in analog continuous time case, amplitudes are belongs to minus infinity to plus infinity, any values, and time also belongs to minus infinity to plus infinity, any value. In analog and discrete time, analog amplitudes minus infinity to plus infinity, any value, and the time is integers, finite set of integers. It need not be finite, countably infinite, but they are integers. And digital, in digital amplitudes are finite set. Continuous time, the time is continuous, so time belongs to minus infinity plus infinity. It can take any value between minus infinity and plus infinity. So the signal has to specify at each and every point of time because it is a continuous time signal. And digital, discrete time, amplitudes, finite set, time, discrete, that is integers. Okay. This is the summary of analog, digital, and continuous and discrete time signals. Okay. Next, another classification, the third type of classification, uh, deterministic and non-deterministic signals. Deterministic and non-deterministic. I will give you a simple definition for deterministic. If it is possible to write a mathematical expression if it is possible to write a mathematical expression for a signal, then that signal is called deterministic signal. Okay. Example, a sinusoidal signal, a rectangular signal. All the signals I have discussed earlier, a step signal or ramp signal. We are giving a mathematical expression for them. U of t equal to 1 for t greater than 0, 0 for t less than 0, like that. But for non-deterministic signal, it is not possible to write an exact mathematical expression. Okay, for example, noise in communication. Okay, you cannot write a mathematical expression for a noise. Okay, n of t. You don't know n of t, but you know the statistical values. That is, so you can estimate them by repeated number of experiments. So this is a random signal, or non-deterministic signals are also called as random signals. Okay, so what can we do for random signals if we cannot write the mathematical expressions? So we can simply estimate them. Okay, so that is their PDFs and CDFs are possible. Probability density functions, cumulative distribution functions. Okay, I will discuss all these things when I discuss the random variables and random processes in communication. These are one of the simple classification. And the next classification, is periodic and aperiodic. This is very important for the exam point of view. Discuss more in detail. Periodic and aperiodic. First one, periodic. What is a periodic signal? If a signal x of t is repeated at a period capital T, or x of t equal to x of t plus r minus n into t. Okay, so x of t is repeated for all t. Okay, with a period capital T. and the signal must be from minus infinity to plus infinity. So minus infinity to minus infinity less than t less than infinity. So the signal must be repeated with the period t from minus infinity to plus infinity. Okay, this is important. Minus infinity to plus infinity. So for example, let's say and so on. 0, capital T, 2t, minus t, minus 2t, and so on. This is x of t. So this is repeating the period capital T. Okay. So and the signal is exist from minus infinity to plus infinity. Suppose one signal, some x1 of t is there. T is like only repeated in positive, and it is 0 for negative values. 0, let us say capital T, 2t, and 3t, and so on. This is repeating. So the signal must be repeated from minus infinity to plus infinity. Okay. So, but here minus infinity to plus infinity, it is not repeating. So this is not a periodic or aperiodic, but this is a periodic signal. Okay. So one period of the signal is repeated from minus infinity to plus infinity. Then it is a periodic. Here from minus infinity to plus infinity, the period of the one single period of the signal is not repeating. Okay, only positive side it is repeating. That is not a periodic signal. It has to be present from minus infinity to plus infinity, and that too it has to be satisfy the condition. It is x of t equal to x of t plus or minus n t. Where n is an integer. This x of t must be satisfy this condition. X of t plus or minus n into t. Okay. If it is not satisfying this condition, then it is a periodic signal. If x of t is not equal to x of t plus or minus n into capital T, then x of t is aperiodic. That's it. Okay. I will give you some examples, periodic and aperiodic signals. First example. Let us say cos 2t, x of t equal to. Okay. So I don't know what is the period of the signal. I will find out. So x of t plus capital T equal to x of t. Okay. Then x of t is a periodic signal with period capital T. What is x of t? Cos 2t. Substitute cos 2 in place of t, t plus capital T. it equal to x of t. From here x of 2t plus 2 times of capital T. That is x of t, the x of t is cos 2t. Okay. From here, at what time we will get both are equal. So if 2 capital T is, let us say if 2 capital T is some integer multiples of k times 2 pi, then sin, suppose k equal to 1, sin 360 plus theta, sin 360 plus theta, cos 360 plus theta is cos theta. Okay, 2 pi is a 360 degrees. Or suppose k equal to 0, then cos of 2t plus 0 is cos 2t. K equal to 1, cos 2 pi plus theta is cos theta. K equal to 2, cos 4 pi plus theta is cos theta, and so on. So the period of the signal is t equal to k times pi, and I want to find out the fundamental period. Fundamental period is the least value of k. Here the k is 1, 2, 3 and so on. If k equal to 0, if you substitute k equal to 0, cos 2t equal to cos 2t. Okay, so you won't get some other signal. Okay, t equal if k equal to 0. So k equal to 1, 2, 3 and so on. So what is the fundamental period? The fundamental period is the least value of k. The least value of k. Okay. So what is the least value of k? K equal to 1. So t equal to pi. Here in this case, the period is t equal to pi. So for cos 2t, the period of the signal is pi. Okay. Similarly, we will find out the period for two signals, that is generalized signals, cos omega naught t, sin omega naught t, e power plus or minus j omega t. First I will discuss for continuous time signals, and then I will go for discrete time signal. Okay. So in continuous time signals, so x of t equal to cos omega naught into t. So we want the period of the signal, fundamental period. So x of t plus capital T equal to x of t. Okay. So what is x of t plus capital T? Cos omega naught t plus capital T equal to cos omega naught t. This is cos omega naught into t plus omega naught into capital T. This is cos omega naught t. If this omega naught into capital T, so this term, if omega naught into capital T equal to some k times 2 pi, then we will get 2 pi into k plus theta equal to cos of 2 pi k plus theta equal to cos theta only. So if omega naught into capital T equal to k times 2 pi, where k is integer, k equal to 1, 2, 3 and so on. So then it is a periodic. And what is a period? T equal to 2 pi by omega naught into k. And what is a fundamental period? Fundamental period is the least possible period. The least possible period is obtained at k equal to 1. So that is t equal to 2 pi by omega naught. Okay. So for all the signals like cos omega naught t, cosine signals, cos of some omega naught into t, then the period t is 2 pi by omega naught. And sin omega naught t also same, x of t equal to x of t plus capital T. What is x of t? Sin omega naught t, that equal to sin omega naught t plus capital T, that equal to sin omega naught t plus omega naught capital T. Same here also, if this omega naught into capital T equal to k times 2 pi, integer multiples of 2 pi, then you will get sin integer multiples of 2 pi plus some theta equal to sin theta only. So here also the t equal to 2 pi by omega naught into k. K equal to 1, 2, 3 and so on integers, and fundamental period t equal to 2 pi by omega naught plus fundamental period is the least possible period of the signal. The least possible period of the signal is 2 pi by omega naught into 1, the k equal to 1. So for both cos omega naught t and sin omega naught t, the fundamental period t is 2 pi by omega naught and e power plus or minus j omega naught t. This case, so x of t equal to e power plus or minus j omega naught t. X of t plus capital T, let us see capital T is the period of the signal, e power plus or minus j omega naught into t capital T. So if x of t equal to x of t plus capital T, then it is the periodic signal. What is x of t? E power plus or minus j omega naught, e power plus or minus j omega naught into t plus omega naught into capital T. This can be written as e power plus or minus j omega naught into e power plus or minus j omega naught capital T. If this value is 1, then e power plus or minus j omega naught equal to e plus or minus j omega naught. Same signal will come. Then it is a periodic. So what is the condition to get this one? That omega naught into capital T equal to 2 pi k. This also, here also, this omega naught into capital T equal to 2 pi times of 2 pi into some integer. Why? E power j 2 pi k is e power plus or minus j 2 pi k is cos 2 pi k plus or minus j sin 2 pi k. What is cos 2 pi k? For k equal to 0, 1. For k equal to 1, cos 2 pi 1. For k equal to 2, cos 4 pi 1. So cos 2 pi k value is 1. And plus or minus j, sin 2 pi k value 0. That is 1. So if omega naught into capital T equal to 2 pi k, then it is a periodic signal. And what is the period? Same as above. So T equal to, the fundamental period T equal to 2 pi by omega naught here also. So for all these signals, cos omega naught t, sin omega naught t, e power plus or minus j omega naught t, the fundamental period t is 2 pi by omega naught. Okay. Next, suppose discrete time signals. For discrete time signals, x of n equal to x of n plus capital N for all n belongs to minus infinity to plus infinity. It also has to repeat from minus infinity to plus infinity. The fundamental component of the fundamental period of the signal is repeated from minus infinity to plus infinity. Okay, same as the continuous time case, but the condition is x of n equal to x of n plus capital N or x of n plus some integer. let us say some r is an integer multiples of n, where r is an integer. Okay, here period is capital N. Capital N is the period. Okay, so for example, discrete time case, this is n. We'll do aperiodic also. Suppose 0, 1, 2, 4, 5, 6, 7. Okay, at 0 we have value 1, 1, 2, 2, 3. Okay, and at 3 again it is 1, to 4 it is 2, to 5 it is 3, and again at 6 it is 1, 2, and 3, and so on. Same here also. So 0, 1, 2. So this is the period. Period is 0, 1, 2. What is the length? 3. 3 is the period. Okay. Same. Whatever 0 at 3. And this is 1. This is 2. This is 3. Similarly repeated. Negative side also repeated. Positive side also repeated. So this is a periodic signal. Here what is the period? Okay, that is important. What is the period? This is repeating from 0 to 1, 2. Okay, and 3 to 5. How many samples are there? Equal equal to 3. So the period is 3. 3 samples is the period. And for the aperiodic signal, I will give one example. 0, let us say 1, 2, 3. 1, 2, 3. 1, 2, 3. The positive side is repeating, but the negative side is it is not repeating, like this. Okay, so it is not repeating some arbitrary values. Okay, so it has to repeat both negative and positive side. Okay, here x of n, so let us say x1 of n. So this is a period, the periodic signal is orange one. This green one is not a periodic. This is a periodic signal. Okay. Next. So here also I will discuss some important signals. Those 3 signals. Cos omega naught n, sin omega naught n, e power plus or minus j omega naught n. Okay, cos omega naught n. So x of n equal to x of n plus capital N. This is the condition. Cos omega naught n equal to cos omega naught n plus capital N. Okay, so I will expand this. Cos omega naught n plus omega naught capital N. cos omega naught t. So this is omega naught capital N plus some theta. Okay, cos omega naught n equal to cos omega naught n plus some omega naught into capital N. If this omega naught in capital N is integer multiples of omega naught into capital N is some k times 2 pi k, then this is periodic. Okay, so because 2 pi times of k plus some omega naught n theta equal to same cos theta, then it is periodic. So here additional constraint is capital N, because it is discrete time signal, capital must be integer. Okay, capital N must be integer. So n equal to, here from this, 2 pi by omega naught into k, where k is integer. Okay, so n also should be integer. Okay, this is also a condition. So n equal to 2 pi by omega naught into k. Next, same thing will happen in sin omega naught n also. So okay, let's question x of n equal to x of n plus capital N sin omega naught n equal to sin omega naught n plus capital N, that equal to sin omega naught n plus omega naught capital N. Here also, if omega naught into n equal to 2 pi times of integer multiple, n equal to 2 pi by omega naught into k. Here we must have n is integer and k anyway integer multiples. So k should be integer 1, 2, 3 and so on. Here also k equal to 1, 2, 3 and so on. Here also e power plus or minus j omega naught n. Take e power plus or minus j omega naught n equal to e power plus or minus j omega naught n plus capital N. E power plus or minus j omega naught n into e power plus or minus j omega naught capital N. This has to be 1. So this term, this exponential term should be 1. So when it is 1, this omega naught into n is same, k times 2 pi, where n is period of the signal, that equal to 2 pi by omega naught into k. Okay. Here k equal to 1, 2, 3 integers and n must be integer. Okay. So n how to calculate? So how to calculate n? N must be calculated from k values. Okay. So k should be taken such that n must be integer, and that too we need to find the fundamental period. So the smallest value of k at which the n has to be integer, the smallest value of integer appear. Okay, that is the fundamental period. When I discuss the problems, so it will get clear. Okay, discuss the problems here itself. The first problem, say, to find out the periods, of the signal. Let us say sine 4 pi t, and a second cos 8 pi t, and a third e power j 8t. Okay, directly capital T fundamental period. Period means fundamental period. Directly sine omega naught t. This is omega naught. So directly 2 pi by omega naught. That is 1 by 2. Here also 2 pi by omega naught 8 pi. That is 1 by 4. Here also 2 pi by omega naught is pi by 4. That's it. Okay. Second case. Second example. Sine 4 pi n. Okay, I will take this as 2 1. 2 example cos 8 pi n. I'm giving the same values here 8 pi 2 pi. So I want to show you some difference here. E power j 8 n. Okay, and one more. Okay, this is third one, and one more also I will give you. Okay, at the end of. Okay, first find out this n equal to 2 pi by omega naught into k. So what is 2 pi by omega naught here? 4 pi into k. That is 1 by 2 into k. Yeah. We'll discuss these two problems in the next slide. So here n equal to k by 2. Here we got n equal to k by 2. That is, let us say 1 by 2 into k. For what values of k, n must be integer. So suppose k equal to 1. K is ranging from 1 to some integer values. Yeah, 1, 2, 3, 4, 5 and so on. Suppose k equal to 1. K, if you substitute k equal to 1, you will get some least value. So n equal to 1 by 2. N equal to 1 by 2 for k equal to 1. But n is not integer. N equal to 1 for k equal to 2. Here n is integer. Here integer. Here n is not integer. So what is the fundamental period? Funda period is n that equal to 1. Okay, not 1 by 2. Because this is discrete time signal. For discrete time signals, they must be integer. Okay, so the least possible integer we will get at k equal to 2. That's it. And the next cos 8 pi n. So cos 8 pi n. So n equal to 2 pi by omega naught into k. 2 pi by omega naught is 8 pi into k. Here k by 4. So at what value of k we will get for smallest integer? For k equal to 4 only. So for k equal to 4, we get n equal to 1. Okay. And this is the fundamental period. For k equal to 8, n equal to 2. That is not fundamental period. That is also period, but that is not fundamental period. Okay. And I gave you one more signal e power j 8n. So here omega naught is 8. So n equal to 2 pi by omega naught into k. That is 2 pi by 8 into k. So n equal to pi by 4 into k. But here pi is irrational number. Okay, never get integer. So e power j8n is not a periodic. It is not a periodic signal. So it is aperiodic. Okay. So I want to put some additional constraint on uh, finding the n value period of the signal, discrete time signal. So where n equal to 2 pi by omega naught into k. So the k by n equal to omega naught by 2 pi. This k by n ratio must be rational. Okay. Otherwise we won't get n as integer. Okay. K by n must be rational. That is an additional constraint for discrete time signals. Okay. So these are some important things. These are all, and I want to discuss some more examples where if we add two signals, what is the fundamental period for them? Okay, I will discuss those things in the next lecture. I'm going to stop now.